In this section, we're going to look at redox titrations. Titration is a process of chemical analysis in which the concentration of an unknown analyte, the substance that's being analyzed, is determined by having it react with a known quantity of a substance with which its reaction is precisely known. The known substance that's added is called a titrant. The titrant is added in small increments until a visible change indicates that all the analyte has reacted. Acid-base titration will be studied in a later unit. Here, we're going to study redox titration. All right, let's look at some steps that walk us through the process of a redox titration, but know that there are some visuals and several examples coming to apply these steps. So they may not make a lot of sense up front, but we will refer back to them. So the first thing we do is we determine something we can titrate our analyte with. So a titrant is determined that will react in a predictable way with the analyte. And in this instance, there must be a visible indicator when additional titrant does not result in further reaction. We need a balanced redox reaction so that we can determine the proportion of titrant to analyte consumed. And we need a known volume of solution containing the analyte in a flask. Then we add a known volume of the titrant to a burette, so it can be added drop by drop to the flask. The titrant is slowly added until the reaction stops. The volume of the titrant consumed is determined. The moles of analyte that reacted are determined from the balanced equation, and we can divide the moles of analyte by the volume of the total solution to yield the concentration of the analyte in the solution. In this image, the analyte is in the solution contained in the flask, down here labeled by this number 1. The titrant is in the burette, so we know a lot about what's in the burette. This is the titrant. The titrant is added drop by drop. You turn this little stopcock and drop by drop, titrant is added until there's an indication that all the analyte has reacted. Maybe a color change. You can see there's a little bit of pink here. So maybe it's a color change. The burette allows for an exact measurement of the volume of titrant consumed. All right, let's walk through an example of this kind of titration step by step. Potassium permanganate, KMnO4-, is an excellent titrant because it has a bright purple color, but its reaction product, which is Mn2+, manganese 2+, is colorless. So we could see the titration happening as we go from purple to colorless. If, when reacting with an analyte like iron 2+, manganese 2+ is formed, the solution will remain clear as long as the reaction is maintained. When all the iron 2 is consumed, the purple color of the titrant becomes visible in solution, indicating the end point of the titration. Let's examine a titration of potassium permanganate with iron 2 nitrate in an acidic medium. Here's the balanced equation without the spectator ions potassium and nitrate. So I'm showing the balanced reaction here, 8H plus MnO4- plus 5Fe2+, produces 5Fe3+ plus Mn2+, and 4 waters. From this, it can be seen that during the reaction, there will be a 5-to-1 ratio of iron 2+ to MnO4- consumed, right? This will get consumed 5 times faster. All right, so here's our question. A 5 molar solution of potassium permanganate, 5 moles per liter, is titrated against a 200 milliliter solution containing an unknown concentration of Fe2+ ions. So in our burette, we have 5 molar solution of K+ and MnO4- ions. And we're going to titrate that drop by drop into a flask that has some unknown concentration of iron ions, and we know that there's 200 milliliters in there. After 20 milliliters of titrant, that would be the MnO4-, have been added, the solution begins to turn purple. What is the concentration of Fe2+ ions in moles per liter? So first, we need to determine how many moles of titrant have been reacted. All right, so we can see here that it says the answers on the next page, but let's work this out first. So we're determining moles of titrant, and in this case, that would be of interest to us is the MnO4-, because that's the part that's not a spectator. So remember that 5 molar is moles per liter. So we have 5 moles per liter, okay? And how much of it did we add? We added 20 milliliters, so 0.020 liters. That'll tell us how many moles of titrant we reacted. So 5 times 0.02, pretty straightforward. 0.1 moles of MnO4-. Okay, so in this next slide, I've carried over my answer from the previous slide. Now let's use the balanced chemical reaction to find the moles of iron 2+ that reacted. So first of all, if I know I reacted 0.1 moles of MnO4-, 5 moles of Fe2+ react for each 1 mole of MnO4-. And that just comes from right here, looking at these coefficients in the balanced equation. And so 5 times 0.1 is 0.5 moles of Fe2+. Okay. 0.5 moles of Fe2+. All right, and then finally, what is the concentration of the Fe2+ ions in the solution? So one big thing to note here is concentration is moles per liter. So we discovered in the previous slide that we had 0.5 moles of Fe2+, and how much of a solution of iron ions did I have? I had 200 milliliters, so that would be 0.2 liters. So 0.5 divided by 0.2 is 2.5 molar. That's our concentration of iron ions in the unknown solution. And just as one final summary, we have the number of moles of our MnO4-, moles of our iron, and we used that to find the concentration of the iron ion, 2.5 molar.